Hi, everybody. In this lecture, I'm going to talk about an application for some of the Fermi physics that we've been discussing so far, and that's white dwarfs. So to do this, I'm going to discuss problem 23 in chapter 7 of Schrodinger's thermal physics, which is the text that we're using for our Physics 3230 course. Now, a little front matter first. Of course, white dwarfs, there's an image of one shown here that's from NASA, and you can sometimes see them at the center of planetary nebulae. They're what happens when a star reaches the end of its life cycle. So when smaller stars die, they first expand as a red giant, and then when they run out of fuel in their cores, they collapse back on themselves. And what's left from this collapse is the white dwarf, and these are very hot objects. Now, what happens is, and this is a quote here from Wikipedia, electron degeneracy pressure halts that gravitational collapse of a star if its mass is below the Chandrasekhar limit, which is 1.44 solar masses. So, of course, this is what's going to happen to our sun. So this electron degeneracy pressure, and we derived an expression for that electron degeneracy pressure in our last lecture. This is the pressure that prevents a white dwarf star from collapsing. So if a star exceeds that limit, and without significantly generated pressure, it will continue to collapse to form either a neutron star or a black hole, because the degeneracy pressure provided by the electrons is weaker than that inward pull of gravity. Okay, so let's talk about white dwarfs and do this problem 23 from chapter 7 in Schroeder. Okay, now this is kind of a lengthy problem, but I think it's exciting. It's an exciting one, nice application. So let's go through it. So this is quoting Schrodinger's problem 23. A white dwarf star is essentially a degenerate electron gas with a bunch of nuclei mixed in to balance the charge and provide the gravitational attraction that holds the star together. In this problem, you will derive a relation between the mass and radius of a white dwarf, modeling the star as a uniform density sphere. White dwarf stars tend to be extremely hot by our standards. Nevertheless, it's an excellent approximation in this problem to set T is equal to 0. And we'll discuss more about that in a minute. So first, show that the gravitational potential energy of a uniform sphere is minus 3/5 gm squared over r. Okay, now I have a confession. I am completely unwilling to write out the slides for all of this. So I'm going to use my iPad. So I'm going to stop share here. And then I'm gonna share my content on my iPad. Okay. Okie doke. So pulling up my iPad, we're gonna do this part A. Now, remember from introductory physics class that gravitational potential energy is given as minus g big M little m over r. And this is if you have two masses, big M and little m, that are separated center to center by some distance r, okay? But we're going to apply this in a kind of different way, and we're going to find the self-gravitational potential energy for a sphere of mass m. So what we're going to do is we're going to integrate this expression, okay? So here we have minus g big M times dm over r. So what we're going to do is envision that we keep adding mass, okay? So we start off with some ball, and then we add a little ring of mass each time until we're up to the total mass of the object, okay? So this is what we're going to do. We're going to keep adding mass until we reach m total. But of course, it's difficult to integrate over mass. Instead, we want to integrate over a spatial coordinate. And we're going to use the density rho of our white dwarf star times dV. Okay, so dm is equal to rho dV, where dV is the differential volume element and rho would be our density. Okay, we're going to use the idea that we have a uniform density for a white dwarf star, which is admittedly an approximation. Now, dV here will be 4 pi r squared dr. And that's because if we add a little layer to it, okay, if we add this layer indicated here with squiggly lines, then the volume of that layer that we add would be the surface area of our sphere 4 pi r squared times how thick our layer is dr. Okay, so that's our dV. Okay, so plugging in now, u would be equal to, we're going to integrate from 0 to our final radius, big R, of our white dwarf star of minus gm over r times rho times 4 pi r squared dr. All right. Okay. So this is equal to, I can pull some constants out. So I've got minus g rho times 4 pi out front. And then I'm integrating from 0 to r of m r dr. Okay, now why did I leave the m in? Well, the truth is that m is also a function of R2. Okay, in fact, if you use the density, m is equal to the density times the volume, which would be the density times 4/3 pi r cubed. So the mass increases as we add layers onto our little sphere. And we've got to count that too if we're doing our self energy here. Okay, so that means that I can write then minus g rho times 4 pi times the integral from 0 to r, and then plugging in rho times 4/3 pi r cubed times r times dr. Okay, now that means that I've got some more constants to pull out front first. So I've got minus g rho squared times 4 pi times 4 pi over 3, right? And then inside, I'm just integrating r to the 4th dr. Well, that's a pretty easy integral. Integrating r to the 4th is just 1/5 r to the 5th. So that's nice. So now I have minus g rho squared 4 pi times 4 pi over 3. Okay. And then integrating that, I would get big R to the 5th over 5. Okay, because I'm integrating from 0 to r. Okay. Okay, now my final derivation, though, it didn't say anything in the proof about leaving it in terms of rho, did it? No, it left it in terms of the mass and the radius, right? So we're going to now have to switch. So since rho is equal to the mass divided by 4/3 pi r cubed, then I can solve. And rho squared would be equal to m squared times 9 over 16 pi squared r to the 6th. Okay, and I'm going to plug that in here. Okay, I'm going to plug that in there. So when I do all that, I get minus g times m squared 9 over 16 pi squared r to the 6th times 4 pi times 4 pi over 3 times r to the 5th over 5. Now, it turns out that when I simplify that, cancel out all kinds of stuff, what I end up with is the relatively simple expression of minus 3/5 times g m squared over r. And that's my u. So yay me, I did it. I proved that my self-energy there was minus 3/5 g m squared over r, just like it asked me to. Okay, great. So that was part A. That was part A. So let's look at the other parts, okay? All right, part B says, assuming the star contains 1 proton and 1 neutron for each electron, and that the electrons are non-relativistic, show that the total kinetic energy of the degenerate electrons equals U kinetic times 0.0088 times this mess here, h squared, big M to the 5/3 divided by the mass of an electron divided by the mass of a proton to the 5/3 divided by r squared. Okay, so that's going to be our next step. Now, first of all, there's a couple of things to understand about this, and that is that they're calling this U kinetic. But what we're doing here is modeling the Fermi energies, the potential energy from the Fermi electrons. That really kind of is a kinetic energy because those fermions are just zipping around in there and they're free. Okay, if you remember previous lectures, we're calling that free. So this is our kinetic energy. And so what we're going to use is the expression we derived in a previous lecture for the energy of a system of fermions, which was 3/5 times n times the Fermi energy, okay? So what I'm gonna do is go back to my iPad. So I'm gonna stop my share here. And I'm gonna share my screen here on my iPad. Okay, so we're going to do now part B. Okay, so U, kinetic, is going to be our 3/5 N E Fermi. Okay, and E Fermi, if you remember from a previous lecture, is h squared over 8 times the mass of the electron times 3n over pi v to the 2/3 power. Okay, that's the 3. Okay, now why is it electrons? Here, remember that it was h squared over 8n times 3n over pi v to the 2/3. And the m was the mass of whatever system of fermions you were considering. So since in a white dwarf, it's the electron degeneracy that's stopping us, then the mass that's out front in our Fermi energy expression will be the mass of the electron. If you were doing something for a neutron star, for example, you would use a different mass out front because you would be considering a different type of system of fermions. Okay. All right, now, basically what we've got here is we want to do a unit conversion of our Fermi energy. So what we have is a density, a mass density for our neutron star. Remember that, or for our white dwarf star. Remember that we had rho was equal to m over 4/3 pi r cubed for our star, right, for our white dwarf star. But we had this as a mass density. And so what we need to do is convert that to a number density, okay? So our mass of our star, if you remember what it said, was it said to assume that for every electron that you had one proton and that you had one neutron. So that means that our total mass could be written as a function of the number of our electrons in our neutron star, or our white dwarf star. So the mass would be n times the mass of the electron plus the mass of the proton plus the mass of the neutron, because the problems distinctly said for every electron you have one proton and you have one neutron. Assume that is true. Okay, fine. So that means that my total mass would be the total number of electrons, n, big N, times me plus mp plus mn. Okay, now the mass of an electron is about 1/1000th the mass of a proton. And so what we can do is we can kind of ignore those electron masses in comparison to our proton masses. And also our proton and our neutron have about the same mass. Now, if you remember in our expression that we're supposed to be deriving here, it had only the expression for, in that expression, it only had the mass of a proton. It didn't have anything about neutron masses. It did have one electron mass, but that would be taken up by this electron mass that's out front here. Okay, so we need to get everything in terms of the mass of the proton. So that means that our mass of our star is going to be n times 2 times the mass of a proton, approximately. Okay. Okay, so if that's the case, then we can write our number of conduction or free electrons here as m over 2 times the mass of a proton. Okay, so now we're able to convert n over v here would then be m over 2 times the mass of a proton divided by the volume of our neutron star. So now I can take this and plug it into my Fermi energy expression. My Fermi energy would be h squared over 8 times the mass of an electron times 3 over pi times m over 2 times the mass of a proton, volume in the denominator there, times 2 to the 2/3 power. Okay, so that's our Fermi energy expression. And now we can plug our Fermi energy into our expression for the total internal energy there, 3/5 times n times h squared over 8 me 3 over pi m over 2 mass proton volume to the 2/3 power. Okay. Alrighty, now n here I can plug in for as well. Remember that I already had that n was the mass of the star divided by 2 times the mass of a proton, right? And so plugging in for that, I have 3/5 times m over 2 mass proton, h squared over 8 mass electron, 3 over pi, m over 2 mass proton, v to the 2/3 power. Okay, I'm getting somewhere now because remember my expression for my kinetic had all these weird 5/3 powers in it. So that's good. I'm getting there now. So now I have, let's pull our factors out front. I've got a mass here, and then I have a mass to the 2/3. So that's a mass to the 5/3. I've got a mass of a proton in the denominator out front, and I have a mass of the proton inside the 2/3. So that's divided by the mass of the proton to the 5/3. See, I'm getting there. Okay, now I also have h² divided by the mass of an electron. All right, and now I have all these strange constants. So I have 3/5 times 1/2 times 1/8, and then times 3/pi 1/2b to the 2/3 power. Okay. All right. Now, my volume is 4/3 pi r³. So if I plug in for that, then what I've got, whoops, awful big, is that 2 in the denominator there times 4/3 pi r³. Okay, now let's look at the r³. So I've got 1/r³ to the 2/3 power. If I take the cube root of 1/r³, I get r. And then if I square it, I've got 1/r². So that gives me m to the 5/3 over the mass of the proton to the 5/3, h² over 2, over MER², and now times all these weird constants, 3/5 times 1/2 times 1/8, and then times 3/pi. And then here I have 3/8pi to the 2/3. Okay, sorry, my handwriting's kind of sucking there in the corner of my iPad. Now, it turns out that if you multiply all this stuff together, you get 0.0088, okay? And so we have proved now what the part B of that question asks us to prove, that we have mass 5/3 times h² over mass proton to the 5/3, mass the electron over r² there, times this constant 0.0088, okay? So, all right, good. So that's our part B. Okay, that's what we were going for. All right, now it says the equilibrium radius of the white dwarf is that which minimizes the total energy. Sketch the total energy as a function of R and find a formula for the equilibrium radius in terms of the mass. As the mass increases, does the radius increase or decrease? Okay. All right. So let's work this one. Now we're coming back to our expression for our total energy. So in order to find the total energy, what we're going to do is sum this kinetic energy here, this 0.088 times h² n to the 5/3 over MEMP to the 5/3 r². We're going to sum that with that gravitational potential energy that we derived on the previous slide, this minus 3/5 gm² over r. So the sum of those two things is going to be our total energy, okay? Now, it says here that the equilibrium radius of the white dwarf is that which minimizes the total energy. So when something is at a minimum, then that means that the derivative of that thing with respect to, in this case, the radius will be equal to 0. And then at that, we can then solve for what the equilibrium radius would be that minimizes the total energy. So that's our strategy, okay? So let's go through this and solve for what the equilibrium radius of the white dwarf is going to be. So I'm going to stop my share here. Okay, so here we go with part C. E total is equal to the kinetic, which is that Fermi energy expression that we had, plus U gravitational, which we derived earlier. okay? So what I'm going to do is I'm just going to write this in terms of some constants because I don't want to be constantly writing out all this crap, okay? And I'm going to focus in on the few things that are really important from those expressions. So I'm going to say that it's beta times m to the 5/3 over r squared, okay? Minus alpha times m squared over r, okay? And basically, our beta here is going to be equal to 0.0088 times h squared over the mass of an electron times the mass of a proton to the 5/3. There you go. Okay, so that's our beta. And then our alpha is going to be equal to 3/5 g. Okay, so that's our alpha. Okay, so now let's take this derivative of E with respect to R and then set it equal to 0. Okay, so if I do that, then I end up with beta m to the 5/3 times minus 2 r to the minus 3, okay, because the derivative of 1 over r squared is minus 2 divided by r cubed, minus alpha times m squared times minus 1 r to the minus 2. And then this I'm going to set equal to 0. And this is going to be my equilibrium radius, okay? So solving for this, I end up with alpha m squared over r squared is equal to 2 beta m to the 5/3 over r cubed. Okay. Now doing this, I can solve for what my equilibrium radius would be. So that would be r equilibrium is equal to 2 beta m to the 5/3 over alpha m squared. Simplifying that expression, I end up with 2 beta over alpha m to the 1/3. Okay. So what this means is that as the mass increases, the radius decreases. Okay, because looking at this expression, as m goes up, the equilibrium radius must go down. Okay. So there's my expression. This gives me a value for my equilibrium radius of a white dwarf star, and I could solve for it, plugging in for what beta and alpha are. By the way, if you solve for what alpha is and beta is in terms of magnitudes, the magnitude of beta, ignoring any and all units, sorry, is 1.8 times 10 to the 6th. And the magnitude of alpha, ignoring any and all units, would be 4 times 10 to the minus 11. So everything here is in SI units, and that gives you an idea of what beta and alpha is, okay? All right, so I'm going to now show you what the plot looks like. I have that plotted out. I did it in, I believe, Maple. So let me stop my share here, share my screen here. Okay, so the sketch, it asks for a sketch of the total energy as a function of R, so we can do that. And that sketch is here. And this is picking on a 1 solar mass object. Of course, it would have to be a mass below the Chandrasekhar limit, which is 1.44 solar masses. But we may as well pick on our sun. And so here's what the plot of the energy versus radius for a 1 solar mass object would look be. And it would come, see, you can kind of tell in this thing that it comes to a minimum value and then it starts to go back up, although the slope after it comes to the minimum is kind of shallow compared to the original slope. Okay, so then from there, it says to evaluate the equilibrium radius for a mass of our sun, 2 times 10 to the 30th kilograms, and find the density. And how does that compare to the density of water? And then also calculate the Fermi energy and the Fermi temperature for this case of the 1 solar mass object, and then see whether or not the T is equal to 0 approximation was valid, okay? So basically, in that case, you know, you're looking at what the temperature of a white dwarf star really is, right? And then comparing it to the Fermi temperature. And if the temperature of the white dwarf star is a lot less than the Fermi temperature, then you can consider it to be a valid approximation to use this. Okay, so that's the idea behind all this. Okay, so I'm going to now use the expression that I've developed for my equilibrium radius, and I'm going to now plug in some numbers and find what the radius of our white dwarf sun would look like. Okay, so the idea here is that we're using this expression 2 beta over alpha m to the 1/3. Okay, and the values of beta and alpha in SI units are 1.8 times 10 to the 6th, and alpha is 4 times 10 to the minus 11, plugging in for all those crazy numbers that we had there for beta and alpha. Okay, so for our one solar mass star that we have the radius of a one solar mass star would be equal to 2 beta over alpha m to the 1/3 power. Here beta is equal to 1.8 times 10 to the 6th in SI units. Alpha is equal to 4 times 10 to the minus 11 in SI units. And plugging in for the one solar mass star, m is 2 times 10 to the 30th kilograms for our sun. So if you plug in for all of that, you get 7.16 times 10 to the 6th meters, okay, which is 7,160 kilometers, okay? Now, I'd like you to note something. This might sound like a lot to you until you consider how big our sun is now and how big the Earth is. So the radius of Earth is actually 6,400 kilometers. So what happens is that when the sun becomes this white dwarf, we're going to be left with this object in the center of our solar system that isn't actually all that much bigger than we are. I mean, that's kind of crazy to really think about. Okay. Now, this, if you evaluate the density would be, rho would be equal to the mass divided by the volume. And that would be 2 times 10 to the 30th kilograms for our mass, estimating that, divided by 4/3 pi, and now times 7.16 times 10 to the 6th meters cubed. So if you find this density value, you end up with 1.3 times 10 to the 9th kilograms per cubic meter. Okay, now that's an incredible density, 1 billion kilograms per cubic meter. Think about it, water has a density of 1,000 kilograms per cubic meter. So this is 1 million times more dense than water. So that's pretty astounding if you think about it. Okay, now in the last part, it said to find the Fermi energy. So here E Fermi would be equal to h squared over the mass of an electron times the mass of our star divided by the mass of a proton to the 2/3 power times 1 over r squared times 9 over 8 pi squared to the 2/3 times 1/8. Okay, so this is plugging in for all of those things that we had in our Fermi energy expression, okay, previously. If you need to pause the video and stare at it for just a second to get this, then that's okay. So if you solve for what your Fermi energy is, then it would be 3.25 times 10 to the minus 14 joules, okay? And that's approximately equal to 2 times 10 to the 5th electron volts, okay? So that's one heck of a Fermi energy. Remember that the Fermi energies for most electrons and metals are just a couple EV, a few EV, okay, like 5.5 EV for silver, for example. So that's a pretty awesome Fermi energy there. And then if you wanted to solve for the Fermi temperature, the Fermi energy is equal to K times the Fermi temperature. And plugging in there, remember Boltzmann's constant is 8.617 times 10 to the minus 5 EV per Kelvin. Then the Fermi temperature would be about equal to 2.36 times 10 to the 9th Kelvin. Okay, so this is our Fermi temperature. Now, from a little bit of research that I did, I found that white dwarf stars have temperatures of about 10 to the 5th Kelvin for white dwarfs. Now it varies, of course, but these are their estimated temperatures based on their spectra that are coming out. And so that means that our Fermi temperature is 10,000 times smaller. I'm sorry, our Fermi temperature is 10,000 times greater. So the temperature of the white dwarf stars is 10,000 times smaller than our Fermi temperatures. And this is why we can use that T is equal to 0 approximation as valid here, because the temperatures of the actual objects are so much less than the Fermi temperature that it becomes a valid approximation. Okay. All right, phew, that was quite the example problem, wasn't it? But I think we ground through it, and I hope we learned something from that example, and then it was interesting to you. So let me know if it went okay, and I'll see you in class.